Yeah, so our next speaker is Hao Cui from the University of Science and Technology in Beijing, where he's currently a PhD candidate. His research is about geochemistry, mainly using hydrothermal diamond anvil cells and fused silica capillary capsules, making experimental petrography and fluid inclusions. Recently, Hao Cui published a paper in geology entitled Forming Sulfate and Rare Earth Element Rich Fluids in the Presence of Quartz. And today he will share some of these really interesting results with us. And with that, the floor is yours, Hao.
Thank you, Aaron. So can you see my screen?
Yes, it's perfect.
It's okay. Okay, thank you. I'm very appreciated about this chance to have this representation. Good afternoon, everyone. I'm Cui Hao, the PhD candidate in University of Science and Technology, Beijing. Today, I'll talk about the sulfate-rich fluids and rare earth mobilization. The Maoniuping rare earth deposit is the third largest rare earth deposit in the world, and it's located on the western margin of Yangtze Craton. There are many sulfate minerals developed in the deposit, such as barite, and moreover, many fluid inclusions in this deposit contain sulfate as dot minerals. During the microthermometry, these sulfate dot minerals melted at about 350 centigrade, and they finally homogenized to the aqueous solution at about 450 centigrade. So this microthermometric results show something weird. First of all, as we all know, the sulfate salts have retrograde solubility. And this means the solubility of sulfates will decrease and temperature increases. For example, the solubility of sodium sulfate in the binary system decreases to below 0.5 mol at 600 centigrade. This leads to a question that why natural gel fluids can dissolve so much sulfate. Moreover, the melting point of solid sodium sulfate is 884 centigrade, and it's still more than 450 centigrade in the water-bearing binary system. But the sulfate dot minerals in the fluid inclusions in Maoniuping deposit melted at about 340 centigrade. So one question arose that why sulfate can melt at lower temperature in nature. The study of these fluid inclusions also showed high solubility of rare earths in such sulfate-rich fluid. But actually, as we know, the rare earth sulfate salts are highly insoluble, while sulfate-rich fluids can transport rare earth element. So what caused so many weird phenomena? In other words, what's the secret ingredient? Here I'll tell you the secret ingredient is quartz. We use bauxite-type hydrothermal diamond anvil cell to conduct our experiments. Sodium sulfate solution were added as a starting material. As temperature increased, the sodium sulfate showed obvious retrograde solubility in this binary system. But things changed as we added quartz crystal into this binary system. Sodium sulfate underwent a series of phase transitions during heating from type 5 to type 3 and then to type 1. The crystals melted at about 270 centigrade. This is nearly 200 centigrade lower than the water-saturated melting point of sodium sulfate. The molten sulfate totally dissolved into the aqueous solution at about 340 centigrade. In order to freeze the molten sulfate, a tiny leak by unscrewing high deck was applied to the sample chamber prior to quenching in order to expel water at high temperature. And this allows the melt to be preserved as glassy sulfide under dry conditions. After the quenching, some amorphous sulfates with foaming structure were preserved, and this indicated that the melt was rich in water. The compositional analysis using inert dispersive spectrometry shows that minor silica was incorporated into the sulfate melt, and probably where the formation of sulfate silicate compounds. And this is consistent with the views proposed by Marshall and Chen. The key transition at 270 centigrade is coupled with the initiation of sodium sulfate melting. This is another high-tech experimental run. It obviously shows that the sodium sulfate precipitated as crystal, but redissolved when sulfate melt formed. The linkage between sulfate melting and the solubility change can be simply explained by the difference in the formation enthalpies of sulfate crystal and sulfate melt, and thus the temperature dependence of the two solubility controlling reactions reversed. In other words, the formation of sulfate melts leads to the poor grade solubility of sulfate, and then the formation of sulfate-rich gel fluids. The molten sulfate can hardly be distinguished from sulfate solid by the appearance, especially at the beginning stage of melting. In some cases, we can observe that two small sulfate melt drops merge into a bigger one. So this can provide strong evidence for the existence of sulfate melt. Also, we confirmed the existence of sulfate melt. The incipient melting can't be easily determined by. We quenched the sample chamber when the phase transition from type 3 to type 1 initiated. Some amorphous sulfate formed in the quenched sample, and this means that the incipient melting is coupled with the phase transition from type 3 to type 1. The different phases of solid sodium sulfate have different Raman spectroscopies. Therefore, they can be easily distinguished from each other using Raman spectrometer. But at the same time, the initiation of sulfate melting is coupled with a phase transition from type 3 to type 1. Therefore, the different phases in this ternary system can be relatively clearly determined. So in order to establish the phase diagram of this ternary system, we use mirabilite as starting materials to ensure the consistent bulk ratio of sodium sulfate to water. Because the dehydration temperature of mirabilite is only 32.4 centigrade, mirabilite should be loaded into the sample chamber in refrigerator. This phase diagram was established from the results of 5 high-tech experimental runs with the same bulk ratio but different bulk densities. Repeated cycles of heating and cooling were conducted during experimental run using gold-lined gasket to confirm that this diagram represents stable assemblages. The rare earth sulfate salts were always thought to be highly insoluble, and this can be clearly observed in our quartz-absent high-tech experiment. The sodium sulfate and neodymium sulfate continuously precipitated from solution. Again, adding of quartz into the system significantly changed the dissolution behavior of neodymium sulfate. sodium sulfate and neodymium sulfate continuously dissolved into aqueous solution. Finally, a sulfate and rare earth-rich fluid formed at about 416 centigrade. The sample chamber was also quenched using the method described above. Energy dispersive spectrometry results show that about 20 µ% of neodymium was incorporated into amorphous sulfate. This result illustrated the mechanism to form rare earth-rich fluids. In quartz and water-saturated system, melting of the eutectic sodium sulfate and the neodymium sulfate system led to the formation of a sodium neodymium sulfate melt. And this induced the progressive solubility of rare earth sulfate. And the sulfate and the rare earth-rich fluids formed finally. And this result of this experimental run clearly demonstrated that the soft iron is indeed a favorable legend for rare earth transportation. The predominance of rare earth sulfate complexes is further confirmed by thermodynamic simulations. The simulations were conducted by HCH software and aim to calculate the solubility of neodymium monazite in fluorine, chlorine, and sulfate-bearing fluids from 300 to 500 centigrade. In the quartz-absent system, rare earth sulfate complexes are neglectable because the sulfate salts will precipitate at high temperatures. More importantly, these fluids have very limited ability to transport neodymium and can hardly account for our formation. The silic-induced solubility change can't be directly calculated because the thermodynamic properties of soft melt and the aqueous sulfate silicon bonds are unknown. However, the major effect of adding quartz to a system is to increase sulfate solubility. So we removed the sulfate solid from HCH system during the thermodynamic. And this can prevent the precipitation of sulfate salts and ensure high sulfate concentration in the system. And in the presence of quartz, the sulfate-rich fluid will be fertile for rare earth element mineralization because the quartz-bearing fluid contains up to 50 ppm of neodymium, with most of them formed as neodymium sulfate complexes. So due to the limitations of available activity coefficients models in simulation, the concentration of sodium sulfate was only set at 2 mol. This is greatly lower than that in natural fluids. Therefore, the calculated rare earth concentration are likely to underestimate the rare earth carrying capacity of natural fluids. Let me give some summaries on this report. Sulfate is highly soluble in crystal gel fluids since it's saturated in silic. The sulfate-rich fluid is good for mineralization, rare earth mobilization. That's all. Thank you for your listening.
Thanks so much, Hao. That was really informative, amazing photographs of your inclusions and really interesting conclusions on rare earth element transport in these sulfate-rich fluids. I'd like to go directly to one of our panelists, Michael Annenberg, if you could unmute yourself and we can get this discussion rolling.
Thank you so much. This is really fascinating. And I think maybe a month ago or something, I gave a talk about my own experiments. And one of the questions we had at the end was, what happens when you have sulfate? And I said, well, I don't have an answer because I didn't have sulfate in my experiments. And you did. And I think it's really nice to show that once you have the sulfate in there, you pretty much form some kind of very low melt where you can stick everything in. So silicon and the elements and sulfate and all of that. But well, I have two questions. One is that the solubility is usually determined by the least soluble phase or mineral. Okay, so for example, if you take neodymium chloride or lanthanum chloride in isolation, they're very soluble. You can just put them in a bucket of water and they dissolve. But once you have insoluble phases around, like fluoride or phosphate or phosphates, then the solubility of the chloride it doesn't matter anymore. Now, so my question is, what happens if you take this and add fluorides and phosphates into the system? Then you stabilize some kind of apatite, for example, monazite. Will you still see high solubilities of elements? Now, I know that you didn't put that in your experiment, but can you say something about that from your experience and working in the field or anything like that? Yeah. So that's my question now. Yeah.
Thank you for your question. So in my opinion, if we add some fluorine into the system, it may induce the precipitation of rare earth element. So it will, of course, reduce the solubility of rare earth element.
Okay.
Okay.
Yeah. Then I also have another question. With my own experiments, again, as I talked about a while ago, it seemed like it was the sodium and potassium, which I also had in those experiments, that made earth elements very mobile. Now, sulfate is indeed something that you see in a lot of earth element deposits, but you don't see it in all of them. There are some deposits in carbonatites where there's absolutely no sulfate. So then the question is it possible that it's not actually the sulfate, it is the sodium, and the sulfate is simply a way to get sodium into the system, and then the sodium is the important thing in mobilizing the earth elements?
Thank you for your question. So in my opinion, also the sometimes the sodium sulfate will be observed in some place, but this may be maybe because the sodium sulfate cannot be preserved. So as we know, the sodium sulfate will be dissolved will be removed easily by water. So maybe in the place without sodium sulfate, it can prove that the sodium sulfate haven't been formed in the past.
Michael, did you see this similar relationships with the sodium chloride system or another complexation for sodium that would indicate sodium is an efficient transport?
Look, so what we have in our paper, and this is the impression I was getting from studies of fluid inclusions, and I think we also have Ben Walter here, who may also say something about what he thinks about it. But yes, it's correct that those things are not preserved in nature, which is why it's very good to have experiments, because then you can say, oh, well, I see that in an experiment. But my feeling was that there's a lot of talk about what's the anionic ligand that allows the transport of earth elements. Is it chlorine or fluorine or sulfate or phosphate, or anyone makes up their own favorite element. And I'm thinking maybe it's not about those anions. Maybe it's that they just serve something, a way to bring in the alkalis into the system, because that was what we saw in our experiment, that it is the sodium that does it. And then, but you need to charge balance the sodium with something. So maybe sulfate is one of them, together with chlorine, together with fluorine and all of that. Now, I think one of the good things about sulfate and why you do actually see it in quite a lot of experiments is that it still remains kind of soluble beyond the other ones, because, for example, if you think of calcium fluoride or calcium phosphate, they are very insoluble, right? I mean, you have apatite, you have fluoride, and once you have them, it's very hard to get rid of them. But calcium sulfate, you know, it's anhydrate or gypsum, it is still kind of soluble. So there's a good chance that once you have sulfate in the system, it still kind of helps and still remains soluble, and then allows the formation of those very low melting brine melts fluids to move the earth elements around. Okay, so something that would not happen if you have if you don't have the sulfate. Okay, and maybe it's, you know, it's not something that's necessary, but it definitely helps, and we do see it in quite a lot of deposits. So yeah, thank you for that, and it's very informative. Yeah.
Yeah, thank you, Michael. How, if you have a comment on the relationship of sodium to the rare earth element solubility or transport, we can say that now. And
sorry, it seems I have no idea about this.
No, I think that's fine. I think it's interesting, both the similarities and the differences between your experiments and Michael's experiments, in terms of what components you put in to the system, and then seeing similar relationship in this rare earth element transport. But with that, I'd like to turn quickly to our next panelist. This is Charlie Beard. I've asked you to unmute, and if you have some insight on this rare earth element.
Certainly do. That was a really, really fun talk, Hao. Thank you very much.
Thank you.
So, yeah, no, that's great. So in experimental petrology, I think I see two broad views that you can use. All experiments are going to be a bit of a simplification of nature, but you can have the type of experiments which you've done here, which is where you take a very simplified system and you look at a process and you try and understand exactly how that process works. And then you have the complete other end of the spectrum, which is what Michael does, which is where you try and use something which is a much more natural composition, and you maybe don't get as clear a picture of the thermodynamics of what's going on, but you can see something which is perhaps a bit more close to what you would see in nature. So my questions, I guess, come to quartz. So you're working in a very simplified system, and you've added quartz specifically. What made you choose quartz, and are there any other components which you've excluded from the system which you think may be important?
Thank you for the question. At the beginning, we add the quartz into the system, mainly to choose the quartz as a pressure sensor.
Okay.
But it's amazing when we add the quartz crystal into the system, and we cannot imagine before. We cannot imagine it will play so important role in the system before we add this crystal into this into our system. So we chose the quartz crystal just for the simple reasons. That's all. Just for the pressure sensor.
Okay. So
and the other components we neglected, maybe carbon dioxide or anything else. So I'm not sure about that.
Yeah, sure. Yeah, so I think that what we can say based on your experiments is that the sulfate can be a mechanism to transport rare earth elements, but it might not be the only one, and it might be very important in a simplified system like this. But as Michael has stated just before, if you add many other components that you would see in nature, the sulfate may play a smaller role than in your system, which you've been working on. So if I had a suggestion for running one more experiment, I would say if you chose a natural carbonatite composition and then you added sulfate, then you could see what the difference was between your simplified system and this. That could be quite interesting.
Okay,
another thing
you.
which
Yeah, no, okay, go on.
Yeah, another question which I have as well is, do you know if there's been any efforts to do direct imaging of interactions between rare earth elements and sulfate, for example, with synchrotron techniques like XAFs or XANES?
Yeah, for this question, my tutor and at the same time, he's one of the co-author, Chen Zhong. He has conducted the similar experiments using the synchrotron, but the paper hasn't been prepared well.
Okay. That'd be interesting to compare. Okay, and then I have one final question, which is we're going to zoom right out to the scale of a carbonatite system in nature. So you need to have a source of sulfate, and you also potentially need to have a source of silica to allow this transport of rare earth metals by a sulfate melt. So silica is quite difficult to get into carbonatites. I don't know very much about saturating carbonatite liquids from highly silica-rich melts. I know that there's been some work in Zurich showing silica undersaturated melts, saturating carbonatite liquids. And I know that there's been some work in Tübingen, Ben Walters here, looking a little bit at contamination of carbonatites by silica, but that tends to saturate common silicate phases like biotite. I guess, where could you get the sulfate from? Where could you get the silica from? And then what does that have as implications for what sorts of systems this mechanism could be important in?
So as for this question, in my opinion, the carbonate can be saturated in silica, and this has been proved by some experiments conducted by my tutor. So maybe that's the answer.
Okay. Yeah, I guess it's
Okay,
just difficult to get the silica in there in the first place, unless you have it from some sort of assimilation or interaction with the core rocks. Anyway, good. Thank you. That was really interesting. And good luck with your next set of experiments.
Okay, yeah, thank you.
Thanks, Hao and Charlie. I think, yeah, this getting silica into carbonatite melts problem is going to be, yeah, this is an issue in comparing real geologic settings to these experimental petrography. But I wonder about other settings, such as these like alkalic deposits, or maybe smaller deposits in the carbonatite things. I'll open the table to Matthias if you have questions or comments for Hao. And if not, we can move into the audience discussion.
No comment from my side.
All right, thanks. So then for the audience discussion, as we did with Honora, you can ask, if you have questions, feel free to ask in Mandarin. We have another Ore Deposits Hub host with us today from University of Science and Technology, Beijing, Boyang Meng, and he will help translate for us from Mandarin to English. Michael has some more comments in the chat, just talking about how the silica incompatibility especially at low temperatures, lower than the decarbonation temperature around 300 Celsius. What was the total temperature range that you ran your experiments to?
For our high-dye experimentals, the temperature range is from room temperature to about 600 centigrade.
Okay, and so then you see this reverse solubility that's present in these systems without quartz. Did you try with different concentrations of quartz to see how this changed the effects of the reverse solubility?
We have conducted the experimental. We have conducted the experiments without quartz. So the sulfate showed obvious retrograde solubility. And for some experiments, we didn't add quartz into the sample chamber, but it's how to say that? But the sulfate still melted at a lower temperature because we before this experimental run, we have conducted experimentals. We have conducted experiments incorporated silic. So there are minor silic in the sample chamber. Also, we didn't add the quartz into the sample chamber. So I think it means even the minor silic will induce the prograde solubility of sulfate, and then the prograde solubility of rare earth sulfate compounds. So as for other experimental runs, we only add a piece of quartz crystal into the sample chamber. So we didn't change the concentration of quartz. So that's all.
Okay, yeah, you made sure that it was quartz silica saturated, at least at that point, because I guess your quartz crystal never fully dissolved in the pictures. So at least at the temperature that your experiments were at, that fluid was theoretically silica saturated. Michael has another comment. I don't know if he can unmute himself. He said his kids are shouting around, but he said that it's interesting to him that this isn't an aqueous solution. It's a hydrous sulfate melt. And I think that's a really interesting point because you do have some formation of aqueous fluid when your primary sulfate mineral, I guess, devolatilizes this. I didn't recall the name, but it has with this hydrous sulfate mineral. And then you said that you, if I recall this correctly, degassed the hydrous component to quench the melt.
Can you repeat the question again, please?
To quench the melt, you said you released the aqueous component to leave just a amorphous solid as your amorphous sulfate solid. Yeah, to expel the water at high temperature.
Yeah.
I think this is interesting, both chemically, but for me, who's not an experimental petrologist, why did you choose this way to quench your experiment rather than a temperature quenching?
Because we think if we just decrease the temperature, the sulfate will the sulfate won't be preserved because the existence of water. So it will become the sulfate crystal again. So if we release the water at high temperature, so the sulfate melt, or we can say the amorphous sulfate can be preserved because there was no water to there was no water in the thermal chamber. So we do this at a high temperature. It's about 500 centigrade, and then we unscrew the high deck, and then to decrease the temperature, and so the amorphous sulfate can be preserved in this way.
No, that's really smart. That's really creative. Michael also is commenting on your creativity. And so then just to follow up on this, the hydrous component of the sulfate melt, was it immiscible or was it dissolved in the sulfate melt? It looks like it was dissolved within, but.
What do you mean? So it's about the amorphous sulfate or anything else? I don't understand about the question.
The water in this melt prior to expulsion, prior to the point where you remove the water, was the water dissolved in the melt or was it a separate phase?
The water is inside the sulfate melt.
Okay.
Yeah.
Thank you.
Thank you.
We're wrapping up this now, so I'll turn just once more to the panel if there's any last questions or comments on this really this novel experiment that Hao has shown us.
Okay, Michael, just write an idea to a future experiment idea for you. How? Repeat the same
Thank
thing,
you.
but try to repeat the same, but add bastanazite. I think I write well. I can write on the chat for you the comment of Michael.